Hi again, Intermediate Algebra gang. Today it's time for Lesson 10.2, Factoring using the distributive property. Again, what we mean by factoring is breaking down a polynomial into its factors, expressing it as a product of monomials and polynomials. And essentially this is the reverse of what we did in Chapter 9. So when we were multiplying polynomials there, now we're going to be reversing that process and not really dividing, but breaking down is probably a better word for what we're going to do here. So let's get right to some examples here. Distributive property is kind of the key thing that we're going to be working with here. So here's the first example, 5x squared plus 35. This is a binomial, of course. Now we're going to look for common factors in each of these terms. So as I look at 5x squared and 35, do they have any kind of a common factor? And yeah, I would say that certainly it is 5. So what I'm going to do is I'm going to pull that out like this, put a set of parentheses, and now I'm going to use the distributive property in reverse. So I ask myself, 5 times what will give me 5x squared? And of course it has to be just x squared. And then 5 times what will give me 35, and of course that is 7. So here's my answer, 5, and then in parentheses x squared plus 7. I broke down this binomial into two parts here, and I have thus factored it. So kind of strange, but it's essentially the distributive property in reverse. Okay, let's do a couple more examples here. So starting with the one on the left, what do they have in common as far as common factors? Well, as I look at 18 and 12, certainly they have a 2 that's in common for factors, a 3. That might be about the biggest one there that I can pull out. So I'm going to pull out, well, how about a 6, come to think of it. Sorry about that. Let's say that 6 is going to be a common factor as far as the numbers go, and look at the n's. One of them has an n squared and another one has an n to the third. What they have in common then has to be n squared. So that's my greatest common factor. I pull that out and then I use my distributive property to figure out what goes in the parentheses. So to get to 18 it has to be 6 times 3. Notice I already have an n squared, so I don't need that again. And then I put my minus sign because that's what's in the original problem. 6 times 2 is 12, and I need one more n here because to get n squared times n has to get me that n to the third power. So there's the factored form of that second one. Maybe you want to pause the video right now and see if you can tackle the third example we have here, and I'll do that for you here momentarily. Alright, so 28 and 42. Now sometimes to figure out, you might need to use our techniques from last lesson to figure out what the greatest common factor is of those two numbers. So I'm going to do this to figure that out. 28 divided by 2 is 14. 42 divided by 2 is 21. Actually 7 will go into both 14 and 21. I get that, then I'm done when I get down to prime numbers here. So my greatest common factor of those two numbers is actually going to be 2 times 7, which is 14. So that's what I can pull out here. Now look at the variables. What do they have in common? Well, they have 1a, it looks like, 1b, not a c though, right? Because only the second term has a c in it. So then it's going to be 2a plus 14 times 3 is 42. So 3b squared c is what goes in the rest of that polynomial. And again, you can check this by simply re-multiplying these to see if they work out. Alright, next example, factoring by grouping. Now, this is kind of difficult. We'll practice this in class some. Not the most important thing in this chapter, or this lesson. But notice this is not a binomial or trinomial. There's 4 terms here. Don't really have an official name for a polynomial like that. And as I look at this, I notice that there are really no common factors for everything. Yeah, there's x's that are in common here, here, and here, but there's no x there. And there's y's in, actually, there are y's in all of them. I could pull one of those y's out. There's not a z in all of them as well, so it makes it a little bit more difficult. So what I'm going to do here, this is called factoring by grouping, and it almost always works out pretty well like this. I'm going to look at the first couple and see if I can find a common factor there. Then I'm going to look at the last 2 terms and see if I can find a common factor there. So first of all, looking at 6 and 9, looks like there the common factor would be 3xy, and then to finish that out I'm going to have 2x plus 3z, like that. Now looking at the second part of that, it looks like, let's see, I'm going to have 2 again, and there's a y squared, right? That's in common. And then I'm going to have 2x plus, sure enough, 3z, like that. Okay? That sign in the middle there, I'm going to say that that was a plus sign instead of a minus sign. I think that might goof us up a little bit. Now here's the tricky part. You might say, well, what can I do with that? That looks worse than it started with, and you're right. But look at this. 2x plus 3z in parentheses there. 2x plus 3z in parentheses there. In a sense now, that's going to be my new common factor of this whole expression. So I'm going to then pull that out and write that in front, 2x plus 3z, like that. I'll put it in parentheses. And then what I have left is this 3xy plus 2y squared. I'll write that in parentheses as well. There we go. And now I'm done factoring that. Now that's kind of a mess, but again, it just emphasizes that whole notion of common factors again, but this time a common factor as a group or as a binomial, like that. So this is kind of strange. The main thing though is the distributive property, where we've used that most of the time up to this point. In multiplying, now we're using the distributive property to break stuff down. So here's a couple of folks here, and has to do with factoring, the x factor, excuse me, and hopefully you're getting a little bit better hang of this factoring stuff, which we'll continue to work on in class. So thanks for watching, everybody, and we'll see you then.